Up until this point, when you were asked to draw an angle bisector, you drew a ray about halfway between that cut this angle in half. Now, to do this the right way, we can actually construct it using a compass. So we can put the end of the compass on B and draw two dash marks like this. So the point where these two dash marks hit, we can then line our compass up again, draw a partial arc like that, line it up again over here, draw a partial arc, and now what we've created is a point that is on the angle bisector. So we can take our ruler or straight edge and connect to make our angle bisector. Now from here I'm going to construct a perpendicular line to BA. So it's going to look something like this. And to do that, I again take my compass and I want to line it up so that I can have two intersections over here. So like this, it intersects right there as well as over here. And I could do the same thing on this side. Make it okay, there you go. Now I'm going to do is line my compass up again on that point of intersection. So I'm going to kind of bold those points so that you can see them. And I want to get an arc that intersects somewhere out here. So let's make that arc. Don't change the compass, line it up again, make an arc. Now what we have is that this point here is on the perpendicular line from this point here. So I can connect those two. And I've just constructed a line that is perpendicular to BA. I can do the same thing on the other side. I'll show you one more time. Again, I line it up at these 2 points. Line it up here. I've got a point made now here where those two arcs intercept, and I can connect it with a straight edge. And now this line is perpendicular. So what I've done is I've found a perpendicular from any point on the angle bisector. I've dropped that line. This line is perpendicular to BC. And what we notice when we take our ruler and we actually measure these two lengths is that this line from our point on our angle bisector to BA, so that perpendicular line, is the same length as this line. Now that I've shown you how to construct an angle bisector and draw these perpendiculars to each side, let's formalize the different theorems that go along with this. The first one is the angle bisector theorem, which says that if we have a point anywhere on this angle bisector, then it is equidistant from the two sides of the angle. So in this case our point is D, and point D is equidistant, DB is equal to DC. So I'll show those with the equivalency marks. Then of course the converse is just the reverse of the angle bisector theorem. So we're just proving this way. We start with the conclusion and give the hypothesis. So in this case we have that if a point is in the interior of an angle, so the point's anywhere in this interior here, and it is equidistant from the sides of the angle, then we can say that it lies on this angle bisector. So in our picture here, DB is perpendicular to AB, and DC is perpendicular to AC, where DB is equal to DC. Then AD bisects angle BAC. Let's put these theorems to work. Now we have two right angles that meet at a point in the center, in the interior on our angle bisector. So we have that these two sides must be equal. So we can set 7x plus 3 equal to 8x. Subtract 7x from both sides, and simple as that, we end up with x is equal to 3. Keep in mind this is from the angle bisector theorem, which allows us to say this. This next example uses the converse of the angle bisector theorem, because here we're given that these two segments are equal, they're congruent. We also have a 90-degree angle, so that must mean that this bisects our larger angle. And by definition of what we know about bisects, that would mean that these two angles are congruent or equal. So we can set up 3x minus 5 is equal to 2x plus 5. Solving for x, we can subtract 2x from both sides, add 5 to both sides, 5's cancel, 2x's cancel, and we're left with x is equal to 10. A good strategy when approaching any of these problems is always to ask yourself, well, do I have the information necessary to conclude certain things about the given picture? And here they want us to conclude that ray AC bisects the larger angle DAB. Well, what we're given is that the two interior equidistant sides, so side CB, is congruent to side CD. Remember that the converse of the angle bisector theorem says that if we have equidistant sides, a point that is equidistant from both sides of this triangle, then we can conclude that this is indeed an angle bisector. So yes, we do have all the information necessary. And what explains it or justifies this is the converse of the angle bisector theorem. When we take and find the angle bisectors of each angle, so this first yellow highlighted one would be the bisector of angle BDC. And you go through this, you find the other bisector, here's the bisector CBD, and then the third bisector of BCD. This point in the center we call the incenter. Now, don't get that confused with the circumcenter from the last lesson. The incenter matches up with those angle bisectors. This is formally discussed in the concurrency of angle bisectors of a triangle theorem, or theorem 5.7 in your book. And this just says that whenever you have the angle bisectors of a triangle, they meet up at this point in the middle. And the interesting thing about this point is that if we drop perpendiculars to all of the sides of this triangle, these perpendiculars are actually equal. So what we can say here is that PD is equal to PF as well as PE. So in an example, if we wanted to know what we can conclude if we know that PF is equal to 32, so this length here, well, we can conclude that PE and PD as well would be 32. So PE is equal to 32 and PD is equal to 32. For the last example, we're asked to find JP in this triangle. P is the incenter, so the center point of this triangle, formed by the meeting up of all of the angle bisectors. So we have the angle bisector here, here, and here, meeting up at that point P, the incenter. And what we know from the last theorem is that PL is going to equal PJ and PN. So we have to use the information that's given, and what we are given is here a right triangle with a hypotenuse length of 25 and a base or leg of this right triangle of 24. So what we can dig out is the Pythagorean theorem. A squared plus b squared equals c squared. In this case, it's the sum of the squares of the legs is equal to the square of the hypotenuse. So we'll call Pn length x, and we'll take x squared plus 24 squared is equal to 25 squared. So we get that x squared plus 24 squared is 576 is equal to 25 squared, 625. Subtract 576 from both sides to isolate the x, and x squared is equal to 49. Solving for x, we can square root both sides. Now keep in mind, whenever you square root, you should take plus and minus, but in this case, x is a length, so you cannot have a negative value, so you can just use the positive here. And x is going to equal 7. So 7 is the length of Pn, which we said was the same as Jp, which is the length we're trying to find. So Jp is equal to 7 as well. And we're done.